In this section, we want to introduce the basic concepts of probability and build our way up to using the counting techniques that we previously established to calculate some different probabilities. We want to start with the most fundamental principle of probabilities, which is that the probability of any event E, which we can represent as P of E, must be between 0 and 1. Or the other way to say that would be that probability has to be between 0% and 100%. So any probability has to be between those two boundaries. The first red flag to look for in any calculation would be as if we get a value that's smaller than 0, greater than 1, we know we've done something wrong in our approach to solving that problem. To look at calculating individual probabilities, one of the first things we need to do is identify the sample space. The sample space is just a list of all possible outcomes from an experiment or a trial. Looking at a couple of simple examples, we could talk about the idea of flipping a fair coin. So a fair coin has two sides. We'll flip it and we'll either get heads or tails. So our sample space has two different possible outcomes. If we looked at a situation where we were rolling a fair die, a six-sided die, then we would have 6 possible outcomes, the numbers 1 through 6, that would be represented on each side of that die. Those are two relatively simple examples, but again, what we're doing is listing out all the possible outcomes. We need some different approaches once we start looking at more complicated experiments, more complicated activities we're looking at. So we can consider identifying the sample space of independent trials or independent events using tables. In example 1, we can take that idea that we already talked about, rolling a six-sided die, and now expand it to rolling 2 six-sided dice. What we'll do with our table is just list in the first column all of the possible outcomes from the first die. And then along the top, we'll list the outcomes from the second roll, that second die. And now we'll fill in our table by choosing the value from the column on the left and the row on the top. What we'll do first is look at each of those rows, and we'll take that 1 and just continue that through each column, and do the same thing with our 2s. And so on for our remaining numbers. And then we'll look at that top row, and we'll take each value and continue it down, so that in our first box now we get the combination where we could roll a 1 on the first die and a 1 on the second die, a 2 on the first die and a 1 on the second die, and so on. We'll continue to do that with our remaining columns, bringing that value at the top down into each of the boxes. And as we're doing this, what we're constructing is the sample space for this experiment, where we roll 1 die and then a second one, and we look at the 2 numbers that we come up with. We could make a slightly altered version of this that would benefit us if what we were interested in was observing the total amount rolled. So meaning we roll two dice, and then add those values together. So what we could do is go through and just total each of these. So if we roll a 1 and a 1, we would get a total of 2, 3, 4, 5, 6, and 7. So again, it would just depend on the problem that we're looking at, if we're looking at the individual numbers or those totals. And we could list the information that's pertinent to the problems that we're trying to answer. And again, what this table is doing is allowing us with these two independent events to map out all of the different possible outcomes, that entire sample space. We can also look at mapping out the sample space for dependent events. So in the case of dependent events, our first outcome impacts the second outcome or other following outcomes, using what we refer to as tree diagrams. In example 2, we have the situation where we first flip a coin. If the result is heads, you roll a 6-sided die. If the result is tails, you draw a card from a standard deck and note the suit. So to construct our tree diagram, what we do is start with a single point, and then we branch out to our first outcome, which would be either heads or tails. If we flip heads, then we have 6 different possible outcomes, because we'll roll a fair-sided die and record that value. If our coin flip comes up tails, then we have 4 different outcomes, because we'll draw a random card from a standard deck and note the suit. So we'll either get a card that's hearts, diamonds, spades, or clubs. And again, what we've done is mapped out the entire sample space, but in this case where we have these dependent events. The first outcome dictates the possibilities that could occur in that second step. So tree diagrams are useful for looking at the sample space for dependent events. They can also be used when we have multi-step events or multi-step experiments. So we have the case of rolling 2 die. Here we had 2 steps, so if there was a third step where after that we have an additional trial that we're looking at.